In August 1958, the United States initiated one of the most secretive high-altitude nuclear test programs in Cold War history, known as Operation Argus. The mission involved detonating nuclear devices hundreds of kilometers above the South Atlantic, far from populated regions and concealed under extreme secrecy. Unlike earlier atmospheric tests, Argus explored how nuclear bursts in near-space environments interacted with Earth's magnetic field and surrounding radiation belts. These experiments aimed to determine whether high-altitude detonations could generate artificial electromagnetic effects capable of disrupting enemy communications. The operation also sought to understand how charged particles released by nuclear blasts behaved when trapped by Earth's geomagnetic lines at orbital distances. Such research was based on scientific proposals that nuclear debris might form temporary radiation belts capable of affecting ballistic missile trajectories. The concept originated from physicist Nicholas Christofilos, whose theoretical work predicted that energetic electrons could become magnetically confined around Earth. His hypothesis suggested that artificial belts might interfere with radar and radio systems, creating new strategic possibilities during the Cold War competition. To evaluate this theory, the U.S. Navy organized a large task force that sailed deep into the South Atlantic, establishing an isolated zone for the tests. The fleet included missile-launching ships, tracking vessels, aircraft, and scientific platforms equipped to measure radiation levels across vast distances. Because the tests required detonations in near-space regions, the military deployed modified rockets capable of lifting small nuclear devices to extreme altitudes. These rockets were launched from the USS Norton Sound, a vessel specially equipped to support high-altitude research missions throughout the 1950s. Scientists from Lawrence Livermore National Laboratory, the Naval Research Laboratory, and other institutions boarded the fleet to conduct measurements. Their instruments included particle detectors, magnetic sensors, radio receivers, and satellite-linked monitoring equipment distributed across multiple ships. All personnel operated under strict classification rules, preventing details of the mission from reaching even senior military leaders not directly involved. The tests took place over the remote South Atlantic to minimize risk to civilian aircraft, shipping lanes, and international observation networks. Because the world had no prior data on nuclear behavior at such altitudes, planners established large exclusion zones to ensure maximum operational safety. Crew members recalled that communication was limited, and many were told only that the mission involved ionospheric research, concealing the nuclear nature of the tests. On August 27, 1958, the first Argus device was launched, reaching an altitude exceeding 160 kilometers before detonating above the upper atmosphere. Instruments recorded an immediate burst of high-energy particles that spread along magnetic field lines, forming a temporary artificial radiation structure. Radio receivers onboard ships detected momentary disruptions, consistent with predictions that nuclear-generated electrons could interfere with communications. 2 additional tests followed within days, each producing distinct particle patterns that scientists studied to understand how long artificial belts might persist. Data confirmed that charged particles could remain trapped for extended periods, although the longevity varied depending on altitude and geomagnetic conditions. These findings validated key aspects of Christofilos' theory, demonstrating that nuclear effects in near-space environments differed greatly from lower-altitude detonations. Measurements indicated that the artificial belts extended thousands of kilometers along magnetic lines, creating radiation zones detectable from distant locations. Scientists also observed how the blasts produced electromagnetic pulses with unique characteristics compared to ground-level or atmospheric nuclear tests. Although the yields were relatively small, their position above the atmosphere allowed energy to spread efficiently across large regions of the ionosphere. This revealed potential vulnerabilities in long-range communication systems and demonstrated how nuclear effects could reach beyond conventional boundaries. After the final detonation, the task force collected remaining instruments and began extensive analysis of the unprecedented data gathered during the operation. Because the mission remained classified, the global scientific community did not learn about the artificial radiation belts until declassification years later. The secrecy reflected concerns that releasing details might reveal U.S. interest in leveraging high-altitude nuclear effects for strategic advantage. Operation Argus thus marked the first and only time the United States conducted multiple nuclear tests far above the atmosphere in a single coordinated campaign. The unusual nature of Operation Argus required coordination across multiple military branches, scientific institutions, and classified intelligence channels. Because no preceding nuclear test had occurred at comparable altitudes, planners relied heavily on theoretical models to estimate the potential scale of effects. These models attempted to predict how geomagnetic fields would redirect charged particles, shaping artificial belts that traced Earth's natural magnetic lines. Scientists warned that even small miscalculations could produce unanticipated radiation zones, making careful monitoring essential throughout the operation. To support this, the Navy deployed ships along a wide arc, capturing particle behavior as electrons streamed across magnetic paths reaching into both hemispheres. The Air Force contributed aircraft equipped with radiation samplers, which flew coordinated patterns to record particle densities following each detonation. These flight missions were tightly timed, aiming to intercept drifting particle clouds without exposing crews to unnecessary levels of ionizing radiation. Meanwhile, tracking stations positioned thousands of kilometers away monitored radio disturbances caused by the tests, gathering low-frequency data for analysis. This global approach offered scientists a three-dimensional picture of how nuclear debris dispersed in near space and how rapidly radiation belts expanded. One significant discovery involved the speed at which electrons migrated along geomagnetic lines, demonstrating mobility far exceeding initial predictions. This rapid movement suggested that high-altitude bursts could theoretically influence communications across large swaths of the planet simultaneously. Researchers found that certain frequencies experienced temporary degradation, providing early insight into how nuclear effects could disrupt long-range radio systems. Despite these disruptions, the yields were intentionally kept low, minimizing risk to satellites, which at the time were still few and in early development stages. Scientists were particularly interested in how the ionosphere responded to injections of high-energy electrons, as this layer played a critical role in radio propagation. Instruments recorded measurable heating and structural changes within the ionospheric plasma, confirming that nuclear sources could alter atmospheric behavior. These findings highlighted vulnerabilities in systems dependent on trans-ionospheric communication, prompting further study into long-term impacts. The operation also revealed how radiation belts formed by Argus behaved differently from natural Van Allen belts, which were discovered only months earlier. Argus belts decayed more rapidly, shedding particles into the atmosphere within weeks, whereas natural belts remained stable over extended timescales. This observation validated theoretical distinctions between artificial and natural radiation environments, offering new insights into Earth's magnetospheric processes. Throughout the mission, strict classification protocols were enforced, with most crew members unaware of the scientific significance behind the measured phenomena. Many personnel only learned the true nature of Argus decades later, when the operation's documents were finally released and its purpose became publicly understood. At the time, secrecy served both strategic and operational goals, preventing adversaries from detecting U.S. interest in high-altitude nuclear capabilities. Strategic planners recognized that revealing details might prompt other nations to pursue similar tests, potentially destabilizing emerging space-related treaties. To manage information flow, post-test communications were sanitized, replacing nuclear terminology with references to upper atmospheric energy experiments. This language allowed data to circulate among authorized researchers without revealing the underlying weapon-based mechanisms driving the observed effects. The need for secrecy also shaped the fleet's movement. with ships maintaining radio silence whenever possible to avoid attracting attention from foreign monitoring stations. Even the test coordinates were chosen to minimize detection by global seismic arrays, which typically identified atmospheric and underground nuclear detonations. Because high-altitude bursts produced weaker seismic signatures, Argus tests remained effectively invisible to standard detection networks of the era. This allowed the United States to evaluate high-altitude effects while limiting geopolitical repercussions during a period of heightened Cold War sensitivity. After the final test, scientists began compiling the massive volume of data, comparing observations across ships, aircraft, land stations, and early satellite receivers. Their combined findings formed a landmark dataset that transformed understanding of nuclear interactions in near-space regions previously unexplored by any nation. As researchers analyzed the Argus data, they discovered that the artificial belts displayed patterned behavior shaped by Earth's rotation and geomagnetic geometry. Charged particles released by the detonations drifted eastward along magnetic field lines, creating elongated radiation zones detectable hours after each test. These belts extended across thousands of kilometers, following predictable arcs that matched theoretical models proposed prior to the operation. Measurements showed that the belts intensified at certain latitudes, where magnetic field strength concentrated energetic electrons into narrow regions. This confirmed that Earth's magnetosphere could trap artificial radiation, forming temporary structures similar in shape to natural Van Allen belts. The artificial belts persisted for days and, in some cases, weeks, gradually decaying as high-energy electrons collided with atmospheric molecules. During this decay, aircraft and monitoring stations recorded changes in radio propagation, noting temporary interference across specific communication bands. These disruptions validated concerns that high-altitude bursts could impair long-range communication systems, including those critical to military coordination. Argus also revealed that nuclear debris behaved differently in near-space environments, because the absence of dense atmosphere prevented rapid particle dissipation. Instead of dispersing quickly, energetic electrons followed magnetic field contours, leading to extended radiation phenomena unexpected at lower altitudes. Scientists documented how the initial explosion produced a shell of ionized plasma that expanded rapidly before stabilizing into magnetically confined zones. This plasma shell altered the local ionospheric structure, temporarily forming reflective layers that changed how radio waves traveled through the region. The effect demonstrated that nuclear activity in near space could artificially modify ionospheric conditions over significant geographic areas. These findings prompted planners to consider how such environmental manipulation could influence radar systems or degrade missile tracking capabilities. Though the yields were small, the altitude amplified their electromagnetic impact, emphasizing how even low-power devices posed strategic implications. Researchers noted that electron densities produced by Argus were not strong enough to cause permanent damage, but sufficiently high to disrupt sensitive equipment. Measurements also revealed variations in particle behavior between the three detonations, influenced by differences in altitude and magnetic alignment. This variation offered scientists deeper understanding of how nuclear-generated radiation interacted with geomagnetic structures under different conditions. One of the most notable outcomes involved the longevity of trapped electrons, which persisted longer than initial conservative estimates had predicted. This extended lifespan confirmed that high-altitude nuclear events could create radiation environments capable of affecting satellites if yields were increased. Although Argus yields were deliberately low, the findings signaled potential risks to orbiting systems as space technology continued advancing. These insights later influenced space policy discussions, as the United States recognized that high-altitude nuclear activity carried implications for satellite integrity. During the analysis, teams cataloged radiation intensities at various altitudes, constructing detailed maps that illustrated the distribution of trapped particles. These maps became foundational references in magnetospheric physics, offering rare empirical data from regions otherwise inaccessible to controlled experimentation. Scientists compared Argus measurements with newly discovered natural Van Allen belts, identifying how artificial belts differed in density, duration, and structure. This comparison enriched understanding of natural magnetospheric processes, bridging gaps between theoretical prediction and observed behavior. The classified nature of the mission meant that only a limited number of researchers had access to the original data during the Cold War. However, the findings circulated within specialized scientific communities, shaping early research on space radiation, ionospheric physics, and electromagnetic effects. Years later, when Operation Argus was officially declassified, the broader scientific world recognized its importance as a landmark in near-space nuclear research. The operation demonstrated how Cold War competition drove rapid advances in understanding the upper atmosphere, geomagnetic fields, and space environment interactions. It also underscored how nuclear technology extended beyond terrestrial boundaries, influencing regions where natural processes were not yet fully understood. The classified findings from Operation Argus soon drew attention within defense research circles, which recognized the strategic implications of high-altitude nuclear effects. Analysts noted that the artificial radiation belts created by the detonations showed potential for disrupting long-range radar systems dependent on stable ionospheric conditions. Such disruptions could degrade early warning capabilities by altering radar reflections, creating temporary blind zones across vast geographical regions. These observations raised questions about whether high-altitude nuclear bursts could be used deliberately to impair strategic detection networks during conflict. Though the Argus tests were small, their electromagnetic reach hinted that larger devices might generate more intense and longer-lasting disturbances. Scientists and military planners evaluated how artificial belts could block or scatter radio waves, reducing clarity and reliability of early warning communication links. Their assessments indicated that engineered ionospheric disruption was theoretically possible, but unpredictable environmental variables limited operational feasibility. Even so, the idea that nuclear effects could influence space environments beyond immediate blast zones introduced a new dimension to Cold War strategy. At the same time, physicists studying Argus data emphasized the operation's contribution to understanding how Earth's magnetosphere responds to sudden energy injections. They discovered that artificial belts tended to form at specific magnetic latitudes, where field lines more easily trapped charged particles from the explosion. This trapping effect produced radiation enhancements that peaked along magnetic field arcs, providing clear evidence for Christofilos' theoretical predictions. Comparable tests at lower altitudes could not replicate these behaviors because atmospheric density would rapidly dissipate electron populations before confinement occurred. Thus, Argus provided the first controlled evidence showing how geomagnetic structures shape particle motion and radiation distribution in near-space environments. These observations became essential for developing early space weather models, which later guided satellite engineers in designing radiation-tolerant systems. Researchers also examined how the artificial belts decayed, identifying loss mechanisms such as atmospheric scattering, pitch angle diffusion, and particle precipitation. Particle precipitation into the upper atmosphere produced faint auroral signatures detectable by sensitive optical instruments aboard ships and aircraft. Though invisible to the naked eye, these emissions indicated that particles were returning to lower altitudes as the magnetic confinement gradually weakened. The rate of decay varied with altitude. Higher altitude belts formed by the tests persisted longer because atmospheric interactions were weaker at greater heights. This provided scientists with a rare opportunity to observe real-time radiation belt evolution, tracing how magnetospheric structures respond to artificial disturbances. Meanwhile, defense officials evaluated the geopolitical implications of Argus, aware that the Soviet Union was expanding missile and space capabilities during this era. U.S. planners considered whether adversaries might attempt similar experiments, potentially weaponizing high-altitude nuclear effects to obstruct strategic communication. Such concerns contributed to later discussions within international arms control communities, seeking to limit nuclear activity in outer space environments. Although Argus remained classified, its findings subtly influenced policy debates that eventually shaped early drafts of treaties governing space-based weapons. Inside the scientific community, the operations data broadened understanding of how Earth's radiation environment responds to both natural and artificial inputs. Comparisons between Argus belts and natural Van Allen belts underscored the delicate balance of geomagnetic processes sustaining Earth's protective radiation zones. These insights offered researchers a baseline for evaluating how solar storms and cosmic events might alter magnetospheric behavior under extreme conditions. Argus revealed that particle injections, even artificially generated ones, could reshape magnetic structures on faster timescales than previously assumed. This realization encouraged more detailed studies of magnetospheric stability, particularly as space exploration and satellite technology continued accelerating. Ultimately, Operation Argus bridged the gap between atmospheric nuclear science and early space environment research, illuminating a region once beyond experimental reach. As Argus data circulated among authorized analysts, it became clear that the operation had produced more than scientific insight. It had revealed new military limitations. Investigators noted that the artificial belts, although temporary, demonstrated how nuclear energy released in near space could propagate across hemispheric scales. This propagation showed the vulnerability of long-distance communication networks, especially those relying on high-frequency bands affected by ionospheric shifts. Because strategic communication infrastructure depended heavily on predictable atmospheric behavior, any disruption carried significant operational consequences. The findings suggested that even small high-altitude detonations could degrade military coordination during the critical opening minutes of a conflict. This realization prompted experts to reconsider assumptions about the stability of command and control systems under conditions of nuclear-generated interference. Although the United States never pursued offensive use of high-altitude nuclear effects, the information shaped evaluations of potential adversarial capabilities. Strategic planners feared that a nation conducting similar tests might attempt to disrupt early warning radars or space-based communication during a crisis. These concerns contributed to a broader understanding that nuclear detonations in near-space environments posed unique geopolitical risks beyond direct blast effects. While Argus itself was defensive and experimental, its outcomes elevated awareness of how high-altitude nuclear activity could influence global stability. Meanwhile, scientists studying radiation patterns realized the operation exposed new layers of magnetospheric complexity previously hidden from observation. They identified subtle wave, particle interactions within the artificial belts that aligned with early theoretical predictions but lacked prior empirical confirmation. These interactions revealed how energetic electrons could resonate with electromagnetic waves, redistributing energy across magnetic field lines over time. Observing this in real conditions allowed researchers to refine models describing how natural radiation belts form, evolve, and decay under varying influences. The operation also provided insight into how solar wind disturbances might interact with radiation belts, informing future studies in space weather forecasting. Because Argus offered rare controlled data, it helped scientists identify how geomagnetic storms could amplify or suppress particle populations in radiation zones. This improved understanding became essential as satellite programs expanded rapidly during the 1960s and 1970s, increasing the need for protective measures. Engineers designing early satellites applied lessons from Argus to shield sensitive electronics from high-energy particles capable of causing system failures. Although technology advanced, the principles derived from artificial belt behavior remained relevant for decades, as space assets became central to global communication. During classified briefings, experts underscored that Argus highlighted the interconnected nature of nuclear science, magnetospheric physics, and global infrastructure. Even small-scale tests demonstrated the potential for cascading effects across multiple technological domains, from navigation systems to atmospheric monitoring. For military leaders, Argus reinforced the need for robust redundancy across strategic networks, ensuring that critical systems could function during severe disruption. This redundancy included alternative communication pathways, hardened electronics, and improved early warning architectures resistant to electromagnetic interference. At the same time, policymakers recognized that repeated high-altitude nuclear tests could damage the emerging space environment, threatening satellite viability. This concern contributed to early debates surrounding the militarization of space, influencing political discussions years before formal treaties were drafted. Within scientific communities, Argus sparked new interest in studying the delicate equilibrium of Earth's magnetosphere, which naturally shielded the planet from radiation. Researchers emphasized that artificially altering this protective structure, even temporarily, offered a glimpse into the vast energy systems surrounding Earth. They concluded that understanding these systems was essential for anticipating natural events such as solar flares, which could disrupt power grids and communications. Through these discoveries, Argus bridged nuclear research with early space weather science, shaping disciplines that later became vital to technological resilience. Despite its secrecy, the operation's scientific impact grew over time, forming a foundation for research into cosmic radiation, orbital safety, and atmospheric interactions. For those who participated, Argus represented a moment when Cold War urgency intersected with scientific opportunity, revealing hidden dynamics of the near-space frontier. As Cold War tensions intensified through the late 1950s, Operation Argus remained deeply classified, known only to select officials with direct involvement in the mission. Its existence was obscured under coded language within Navy reports, masking the nuclear nature of the tests behind references to geophysical research activities. This secrecy reflected national concerns that disclosure might encourage rival nations to explore similar high-altitude experiments, potentially escalating arms competition. Decision-makers understood that if adversaries attempted to replicate Argus, the resulting radiation belts could threaten early satellites essential to global communication. Early reconnaissance satellites, navigation prototypes, and scientific payloads operated within or near regions affected by high-energy particle environments. Disruptions caused by artificial belts could impair onboard electronics, degrade sensors, or short operational lifespans through cumulative radiation exposure. Although Argus yields were intentionally low to minimize such risks, researchers warned that larger detonations could produce effects capable of damaging orbital assets. This realization arrived at a pivotal moment, as both superpowers were actively entering the space age and preparing to deploy new generations of satellites. Scientists briefed military planners that further high-altitude testing would require careful consideration of potential impacts on the expanding orbital environment. These concerns helped shape early guidelines for satellite design, emphasizing shielding materials, radiation-hard components, and protective operational procedures. Engineers integrated these requirements into the first dedicated, whether satellites and early communication spacecraft launched in the decade following Argus. The mission also influenced discussions among policymakers drafting preliminary principles that later formed the basis for international agreements on space activity. Although formal treaties restricting nuclear detonations in space emerged years later, Argus played a significant role in revealing the need for such frameworks. Meanwhile, scientific analysis of the artificial belts continued for months, with teams evaluating how radiation gradually declined as particles lost energy. They observed that particle precipitation differed based on altitude, with lower belts dissipating more quickly due to stronger atmospheric interactions. Higher altitude belts decayed slowly, revealing how sparse atmospheric density allowed energetic electrons to remain magnetically confined for extended periods. These observations aligned with theoretical predictions, but provided the first direct confirmation of magnetospheric behavior under controlled experimental conditions. Researchers noted that the decay process produced faint radio emissions, which were tracked by sensitive receivers aboard ships still stationed in the region. This data offered unprecedented insight into low-frequency electromagnetic phenomena, generated as energetic electrons spiraled along magnetic field lines. The operation's unique environment enabled scientists to measure interactions rarely observed in natural settings due to the unpredictable nature of solar activity. Through Argus, researchers could study particle wave relationships under known initial conditions, improving understanding of magnetospheric resonance mechanisms. These findings informed early models used to predict how natural radiation belts respond to the solar wind, magnetic storms, and interplanetary disturbances. Such models later became essential for protecting astronauts, space-based sensors, and communication satellites from fluctuating radiation environments. At the same time, military planners evaluated whether Argus-like belts could inadvertently impact national assets or foreign satellites during future crises. Because artificial radiation belts drifted along magnetic lines, they could theoretically affect regions far from the initial detonation point. This raised concerns about unintended consequences if high-altitude nuclear tests were conducted without careful coordination or scientific oversight. Argus demonstrated that nuclear activity in near space could produce complex global effects not limited to blast zones, reinforcing the need for strict control. These insights contributed to the emerging consensus that nuclear detonations above the atmosphere posed significant risks to strategic stability and space infrastructure. As analysis deepened, U.S. officials recognized that the operation's results held profound implications not only for national defense, but for international space policy. The mission ultimately underscored that space was not an empty void, but a dynamic environment shaped by magnetic forces, solar energy, and human intervention. As the scientific community absorbed Argus findings, researchers emphasized that the operation marked a turning point in understanding near-space nuclear effects. It demonstrated that even limited-yield detonations produced radiation environments capable of influencing technological systems thousands of kilometers away. These results shaped future risk assessments as satellite constellations grew, making radiation forecasting a central part of mission planning. Engineers recognized that high-energy particles, whether natural or artificial, could degrade electronic components, corrupt data streams, and damage solar panels. The artificial belts generated by Argus became case studies for testing shielding concepts and material durability in extreme radiation environments. These studies later informed design protocols for spacecraft expected to operate within or near the Van Allen belts for extended missions. At the time of Argus, however, much of this understanding remained restricted to classified programs, accessible only to those directly involved in national defense. The secrecy persisted because the artificial radiation data provided insights into nuclear effects that could influence strategic communication technologies. Officials feared that premature release might inspire rival nations to exploit high-altitude detonations to disrupt U.S. infrastructure during crises. Such concerns reflected the competitive climate of the late 1950s, when the Soviet Union was actively expanding its missile capabilities and space ambitions. U.S. analysts monitored Soviet scientific publications, searching for hints that adversaries might have detected the unusual radiation patterns generated by Argus. Available evidence suggested that the tests went largely unnoticed internationally, aided by their remote location and limited electromagnetic signatures. This lack of detection reassured planners that the operation remained concealed, allowing scientists to evaluate high-altitude effects without geopolitical disruption. Meanwhile, Argus data challenged traditional assumptions about the boundaries between atmospheric and space-based nuclear phenomena. It revealed that effects far above the atmosphere could propagate along magnetic structures, influencing regions where nations had little prior experience. This realization framed early debates about whether military actions in near space required new forms of regulation distinct from terrestrial nuclear policy. As the United States advanced further into space exploration, Argus shaped understanding of radiation hazards that astronauts might encounter at high altitudes. Researchers studying early human spaceflight referenced Argus radiation profiles when evaluating safe orbital paths beyond the densest regions of the Van Allen belts. These evaluations contributed to planning for Project Mercury and later Apollo missions, which relied on minimizing radiation exposure during ascent and orbital operations. Although Argus yields were small, the operations data helped identify conditions where radiation levels could spike unpredictably after energetic particle injections. Scientists emphasized that natural solar storms contained far more energy, suggesting that understanding artificial belts also illuminated vulnerabilities to cosmic events. This connection encouraged interdisciplinary research involving physicists, engineers, and atmospheric scientists studying Earth's coupled space environment. Such cooperation laid the groundwork for the emerging field of magnetospheric science, which grew rapidly in the years following the operation's declassification. Within the military, Argus also informed discussions on early warning system resilience, highlighting the need for communication networks less dependent on ionospheric conditions. This led to increased interest in satellite communication systems, which gradually replaced long-range high-frequency radio links vulnerable to geomagnetic disturbances. As satellite technology matured, its reliability became closely tied to understanding how radiation could impair or disable orbital assets during periods of heightened activity. Argus provided early warning that unanticipated radiation increases, whether natural or artificial, could threaten the operational continuity of space-based systems. These insights motivated further research into radiation belt dynamics, satellite hardening techniques, and predictive models to forecast hazardous space weather. By the time Argus was fully declassified, its scientific contributions had already shaped decades of technology, policy, and understanding of the near-space domain. Researchers who later reviewed the original data recognized it as an unprecedented experiment that expanded knowledge of Earth's magnetic and radiation environment. Although initially hidden from public view, the operation's legacy continued to influence how nations approached nuclear policy and space exploration. As declassification progressed, Operation Argus slowly emerged from secrecy, allowing historians to reconstruct the mission's technical and strategic significance. Documents revealed how the operation combined naval logistics, nuclear engineering, and magnetospheric physics into one of the most complex tests of the era. Researchers recognized that Argus represented a rare intersection of Cold War urgency and scientific exploration at altitudes beyond conventional reach. Its data archives offered a detailed snapshot of near-space behavior under controlled nuclear conditions, something no nation has replicated since 1958. The mission's uniqueness stemmed from both its scale and its altitude, as later treaties prohibited nuclear detonations in outer space or near-space regions. The 1963 Partial Test Ban Treaty effectively ended atmospheric and high-altitude nuclear testing, making Argus the only multi-detonation campaign of its kind. This elevated the operation's scientific value, preserving its findings as the sole comprehensive dataset on artificial radiation belt formation. When the data became available to the wider scientific community, it helped validate theoretical models that guided early satellite and spaceflight planning. Scholars studying magnetospheric dynamics used Argus results to refine simulations describing how energetic particles behave in large-scale magnetic systems. The operation's measurements also contributed to the foundation of space weather forecasting, a discipline essential for protecting modern communication networks. As technology evolved, space weather predictions became critical for safeguarding GPS systems, power grids, satellites, and aviation operations from solar disturbances. Argus demonstrated that particle injections, whether natural or artificial, could alter radiation environments rapidly, challenging assumptions about near-space stability. This insight encouraged governments and research institutions to invest in monitoring stations capable of tracking particle flux across orbital regions. Today, global radiation monitoring systems owe part of their conceptual origin to the lessons learned from Argus during its brief but impactful campaign. Historians reviewing the operation noted that its classified nature obscured its contribution for decades, eclipsed by larger and more public nuclear programs. Yet Argus influenced multiple Cold War decisions, including policies aimed at preventing the militarization of space and protecting early satellite networks. Its findings helped demonstrate that nuclear activity above the atmosphere carried consequences far beyond national borders, shaping international security concerns. These concerns later guided discussions leading to the Outer Space Treaty of 1967, which prohibited weapons of mass destruction in orbit or on celestial bodies. Although Argus was not publicly cited during treaty negotiations, many principles embedded in international agreements reflected insights from the operation. Scientists who studied Argus long after its declassification emphasized that the mission offered a rare controlled experiment at the boundary between atmosphere and space. They argued that understanding artificial radiation belts provided key context for evaluating natural risks, including solar flares and geomagnetic storms. Engineers designing spacecraft today still account for particle behaviors first observed during Argus, including drift patterns and high-energy precipitation events. This influence persists because the fundamental physics revealed by the tests remains relevant regardless of advances in satellite shielding and circuit design. Argus also highlighted the complexity of Earth's magnetic environment, demonstrating how interconnected global systems respond to sudden injections of energy. Researchers concluded that even small disturbances could ripple across hemispheric scales, revealing the magnetosphere's sensitivity to external and internal forces. For historians, the mission serves as a reminder that much of Cold War scientific progress occurred in parallel with military priorities, often under deep secrecy. Argus exemplifies how military-driven research sometimes produced breakthroughs that later shaped civilian science, technology, and international policy. The operation also underscores how nations used remote ocean regions as testing grounds during an era when nuclear experimentation expanded beyond conventional limits. While the world never again conducted similar high-altitude nuclear tests, the knowledge derived from Argus remained central to understanding near-space hazards. Its legacy continues through scientific literature, where researchers still reference its datasets when modeling radiation environments for modern spacecraft. Ultimately, Operation Argus stands as a singular moment in history, an experiment conducted under Cold War pressure that revealed hidden dynamics of Earth's magnetic frontier. Though classified for years, its influence endures across scientific disciplines, demonstrating how one secret mission reshaped our understanding of the space surrounding Earth. In retrospect, Argus represents both a bold scientific achievement and a cautionary example of how nuclear experimentation extended into regions once thought untouchable. Its outcomes continue to guide modern policy, technology, and space research, ensuring that lessons from 1958 remain relevant in an era defined by orbital dependence. After Operation Argus was completed, analysts spent years interpreting the mission's extensive measurements, which offered unprecedented insight into nuclear effects in near space. Their evaluations confirmed that artificial radiation belts formed by the detonations behaved differently from natural belts, decaying faster yet producing intense localized impacts. This decay pattern provided essential clues about how magnetospheric structures respond to sudden energy injections, informing many early models of radiation dynamics. Scientists noted that the artificial belts propagated along geomagnetic lines at speeds that exceeded initial expectations, revealing previously undocumented particle behavior. This movement influenced how future researchers evaluated geomagnetic drift, pitch angle scattering, and the long-term stability of trapped electron populations. Data from Argus later helped refine predictions about how satellites might respond during geomagnetic storms, shaping planning for early orbital missions. Engineers used Argus radiation profiles to design shielding strategies for spacecraft, ensuring electronic components were protected from high-energy particle flux. These shielding techniques became essential as satellite networks expanded, supporting navigation, communication, and reconnaissance throughout the Cold War. Argus findings also shaped assessments of nuclear vulnerability, demonstrating that high-altitude bursts could inadvertently threaten critical orbital infrastructure. This revelation encouraged policymakers to advocate for international agreements limiting nuclear activity in space, leading to greater focus on orbital safety. Although Argus remained hidden from public view for decades, its scientific influence quietly expanded through classified briefings and restricted technical reports. Researchers who worked with the original data emphasized that the operation provided the only controlled measurements of artificial radiation belt formation. These measurements became irreplaceable references, as no subsequent experiments allowed nuclear detonations in near space following treaty restrictions of the 1960s. Historians later described Argus as a scientific anomaly, a moment when geopolitical tension enabled a level of experimentation impossible in later decades. When documents were declassified, the operation's significance became clearer, showing how it shaped both strategic thinking and the emerging field of space physics. Argus also influenced studies of atmospheric chemistry, as the decay of artificial belts revealed how energetic particles interact with upper atmospheric molecules. These interactions helped researchers understand natural processes that influence auroral emissions, ionospheric conductivity, and long-distance radio transmission. Military analysts found that Argus confirmed potential risks associated with high-altitude detonations, reinforcing the need to protect communication infrastructure. They concluded that even low-yield nuclear activity above the atmosphere could create electromagnetic environments capable of degrading radar and early warning systems. This realization strengthened arguments for redundancy across strategic communication channels, leading to development of hardened infrastructure during the Cold War. In the scientific community, Argus data continued to circulate long after its declassification, providing benchmarks for radiation belt research worldwide. Modern studies still reference Argus when evaluating particle injection events caused by solar storms, magnetospheric substorms, or cosmic ray interactions. This lasting relevance reflects the unique nature of the operation, which provided controlled conditions that natural events rarely replicate with similar clarity. For engineers designing next-generation spacecraft, Argus remains a historical touchstone, demonstrating how energy released in near space can travel along magnetic lines. This understanding guides mission planning for satellites expected to operate in harsh radiation zones, including geostationary and medium Earth orbit locations. As historians revisit Cold War nuclear research, Argus stands out as a reminder that scientific progress sometimes emerged from missions conducted under intense secrecy. The operation embodies the complexity of an era when military necessity, scientific exploration, and geopolitical caution were intertwined across global programs. Though initially unknown to the public, Argus eventually earned recognition as a landmark study that reshaped understanding of Earth's magnetic environment. Its lessons continue to inform research on radiation hazards, space weather forecasting, and satellite protection, maintaining relevance in the modern technological world. Today, Operation Argus is viewed not only as a Cold War experiment, but as a defining moment in humanity's exploration of near-space phenomena shaped by nuclear energy. Its legacy demonstrates how knowledge gained from a single covert mission can influence generations of scientific development and international policy.